Hello everybody, I'm here doing another Professor Sykes video. I know it's been a long time since I've done one, but I thought I'd come back and I'd do one on momentum. So, the first branch that we're going to look at is this equation right here. Momentum is mass times velocity. Now this is an important one, I think you need to learn it for GCSE. And your momentum is in kilogram meters per second, your mass is in kilograms, and your velocity is meters per second. If you wanted to rearrange this, I've got those there, and literally, I'm sure you're all confident with rearranging equations, so that shouldn't be much of a problem for you there. Just to show how it works, I thought I'd do a practice question. So, in the exam you might get asked, what is the velocity of a car, what is the momentum, of a car weighing 50 kilograms, and it's travelling at 25 meters per second. So, what would you do in this situation? Well, you'd substitute the values into the equation, and you'd have 50 times 25, which is the momentum, which is, just need to work this out, 1,250. And that is in kilogram meters per second. Okay? On to the next branch. So here we're going to talk about conservation of momentum. Now, it's really important to note that this is in a closed system, and most exam questions would say, calculate this in a closed system. But it's important that you're aware that this only applies if it is in a closed system. So there are two ways that kind of momentum is transferred and the conservation of momentum can be applied. So you can have a collision, such as snooker balls colliding. So you hit the white one and it travels at a high velocity with a constant mass, and it hits, let's say, a red that you're trying to hit. And that the momentum is transferred over, and you'll notice that the red one actually starts moving at speed, and the white one still carries on because it still has some momentum left, but at a much slower speed. And unless the white one stops completely, the red one will most likely not travel as fast as the white one did when you hit it, just because the momentum isn't 100% transferred. There's still a bit left in the white one, but most of it's gone into the red one. The other scenario that we could use this in is an explosion, and not necessarily just kind of dynamite or whatever, massive explosion. This could be kind of two weights being pushed away from a single point. Now, this is quite an interesting case, because in an explosion, the original momentum is zero, because it's not going anywhere. There's mass, yeah, but it's not going anywhere, so it's mass times zero, which is zero. But when the explosion happens, you've got bits flying out everywhere, haven't you? And a lot of people would think, well, there must be an overall change in momentum there. However, because both momentum and velocity are vectors, as in with direction and magnitude, oh yeah, that means that parts flying this to the right will have an opposite momentum with those travelling to the left. So, while you might have a kind of 1 kilogram block moving at 5 meters a second that way, there might be a 1 kilogram block moving at 5 meters per second that way, but because that is 5 meters per second, that is negative 5 meters per second because it's velocity. So then you end up with 5 kilogram meters per second, and then you have to add the two together to get the overall. So you got 5 kilogram meters per second, add negative 5 because of the opposite direction meters per second, and you add the two together and you get nothing, which shows conservation of momentum. So you've also got another equation associated with momentum, and that is this one right here. Force is mass times the change in velocity all over the change in time. Now, this one comes from the fact that force is your mass times acceleration, and acceleration is the change in velocity over the change in time. Now, you might see this written differently. It can be written as the way I've done it, but it can also be written as v take u over the change in t, or time. And both are acceptable, but this is just a simpler way of writing it, and it is written that way in this equation, so you might as well write it like that in the acceleration equation. And you substitute the a value into this equation, and you get that F is mass times the change in velocity over the change in time. Now, your mass is in kilograms again, your change in velocity, and it's important to note that it's the change in velocity, not the overall velocity. That's in meters per second. Your force is in newtons, and your time is in seconds. And most often, sometimes they will give you kind of other the values in other units, and and a lot of the time it's time that's in minutes or hours or whatever. So it's important to note that you need to make sure that time is in seconds, as well as mass being in kilograms and velocity being in meters per second. Your force is in newtons, and your force is equal to the rate of the change in momentum. Now, this is important, and it brings us on to our next one here, safety measures. Now, this, I'll do the example while I'm talking about safety measures. So, a crash will mean that your velocity changes very quickly from, if you're in a car crash, say, from kind of maybe 60, 70 miles an hour to 0 in a couple of seconds. So if you substitute this in, you might have a car of 60 kilograms, and you might be going at 70, and then you suddenly crash, and you're going at 0 then. So you have 60 times 70, and then you do this happens in 5 seconds. So if you did that, the force that would be exerted on you, and it's not just exerted on the car, it's exerted on everything that changes velocity in that time. So it would be exerted on you as well. And obviously your mass value would be different. Probably actually this would be your mass value rather than the car. Hope there aren't any, or I bet there aren't any cars that are 60 kilograms out there. You never know. But if you do this, then your force that would be exerted would actually be 4,200 over 5, which is that is 840 newtons. That's a lot of force exerted on you. That could cause death in some situations. So we install certain safety measures in our cars and while we're riding bicycles and things like that. So, you've got airbags and seatbelts in cars, you've got crumple zones in cars as well, and you've got crash mats when you're kind of doing gymnastics if you fall off something from a height. And these increase the change in time. So if you were if an airbag was deployed, it would mean that this change of 70 meters per second would actually happen over a lot longer than 5 seconds. So this force would actually go down. The same goes for bike helmets as well. And it's actually important. It's really important to note, though, that these safety measures take the force for you as well, because they're going at the same speed as you, and while they will most likely have less mass, they have mass, and so they will take a lot of the force for you. And particularly in the cases of bike helmets and seatbelts, you have to replace them after you've been involved in a crash, because otherwise they won't work next time, because they might be cracked, or they'll have been stretched beyond their kind of elastic limit in the case of seatbelts. So they're no longer useful. So they must be replaced every time. But that's all I've got for you guys about momentum. Hope you learned a lot. And in the famous words of Bob Ross, good night and God bless.